A battleship is designed as a honeycomb of steel. The logic of naval architecture dictates that if one compartment floods, the surrounding walls must hold that weight and prevent the ocean from traveling further. This is the principle of watertight integrity. On the morning of December 7, 1941, the USS California was not defeated by the physics of the torpedo alone. She was defeated by a procedural schedule. The ship was at a peacetime readiness posture and, critically, was preparing for an imminent material inspection, so watertight integrity was not at its maximum. The crew was preparing for a material inspection scheduled for the following Monday. To prepare for this assessment, many watertight fittings, doors, hatches, and inspection openings were not fully secured as they would be in wartime, leaving internal boundaries more vulnerable to progressive flooding. Under normal battle conditions, these manholes are bolted tight, creating independent cells of air that provide reserve buoyancy. On this morning, the cells were open. The honeycomb was unsealed. At 8:05 in the morning, 2 Japanese torpedoes struck the port side. The impact tore through the outer shell and admitted the Pacific Ocean into the fuel system. In a sealed ship, this damage is severe but survivable. The holding bulkheads contain the flood. The damage control teams counter-flood the opposite side to correct the list. But the California was not a sealed ship. The water entering the hull did not stop at the impact zone. It surged through the open manholes. It traveled from the fuel tanks into the voids and then into the central engineering spaces. The void space is the most critical passive defense a warship possesses. It is an empty compartment designed to act as a buffer. When a void fills with water, the ship loses buoyancy, but if the void is sealed, the loss is calculated and finite. When the void is open to the rest of the ship, the loss is uncontrolled. The flooding moved faster than the crew could secure the heavy covers. The water rose into the propulsion machinery. The California operated on a turbo-electric drive system where steam turbines turned massive electric motors. As flooding and contamination spread, the ship lost electrical power, crippling lighting and pump capacity at the worst possible moment. Without power, the primary salvage pumps could not operate. Without pumps, the water could not be fought. Over the next 3 days, the battleship did not capsize. She settled. The water weight increased until it exceeded the displacement of the hull. The ship sank vertically, ending her movement only when the keel met the harbor floor. She came to rest in the soft mud of Pearl Harbor, listing 5.5 degrees to port. The salvage engineers arriving at the site faced a geometry problem. The quarterdeck and the forecastle were awash, sitting just below the surface. The main deck was submerged. The ship was not just a wreck, she was a 32,300-ton battleship-sized obstacle sitting on the bottom. The initial survey confirmed the status. The hull was intact enough to be raised, but the internal watertight boundaries were violated. The objective was not just to patch the holes in the side. The engineers had to reverse the consequences of the open manholes. They had to pump out a volume of water that was effectively connected to the ocean outside. To do that, they would have to change the shape of the ship itself. The California was down, heavy with water and fuel, and gripped by the suction of the mud. The engineering team had to find a way to isolate the hull from the sea before they could even attempt to lift the weight. Accessing the interior of the USS California was not simply a matter of swimming through the flooded compartments. The salvage teams faced an environment that was chemically hostile. The ship had settled into the mud at a depth of 40 feet, but the water inside the hull was not clean Pacific seawater. It was a toxic emulsion. When the torpedoes breached the fuel tanks, they released approximately 200,000 gallons of heavy fuel oil. This oil did not just float to the surface, it coated every bulkhead, every ladder, and every piece of machinery. In the unlit interior, the oil created a total blackout. A diver's light could not penetrate the opaque black liquid. But the oil was only the carrier for a more volatile hazard. The California was fully provisioned for war when she went down. Her cold storage lockers were packed with sides of beef, fresh vegetables, and flour sacks intended to feed a crew of thousands. When the power failed and the water rose, the refrigeration stopped. The ship became a sealed steel vessel, incubating tons of organic matter in tropical water temperatures. The decomposition of this biomass produced high concentrations of hydrogen sulfide. This gas is a specific operational hazard in marine salvage. It is colorless, flammable, and heavier than air. It pools in the lower compartments, displacing oxygen. In high concentrations, it does not just cause asphyxiation, it is chemically toxic to the human nervous system. The Salvage manual for the operation noted that the gas presence required strict atmospheric monitoring. Crews entering pumped spaces were required to wear chemically treated masks to prevent immediate incapacitation. The presence of this gas complicated the dewatering process. As the pumps began to cycle, they drew from the bottom of the flooded sections where the water, oil, and decaying organic matter had settled. The fluid discharged by these pumps was so foul that it created an operational radius of nausea. The Salvage log records that the discharge hoses could not simply be vented over the side. They had to be extended and routed far downwind of the working parties. If the wind shifted, the pump discharge alone was enough to force work stoppages on the surface barges. This toxic atmosphere was trapped inside the void spaces and corridors mentioned in the previous report. The open manholes that had allowed the ship to sink now allowed the gas to migrate freely between compartments. The Salvage plan required the divers to enter this black, toxic fluid to seal the hull. They had to navigate by touch, feeling for valves and hatches while submerged in oil that would blind them instantly if their faceplates failed. However, the gas and the oil were secondary to the primary hydrostatic problem. The engineers could mitigate the toxicity with ventilation blowers and masks. They could not mitigate the ocean level with pumps alone. The main deck of the California was submerged. If the pumps lowered the internal water level, the ocean would simply flow in over the gunnels to replace it. The ship was not just a flooded vessel, it was a submerged container with no lid. Because the weather deck was submerged, the Salvage team built large wooden cofferdams to raise the effective waterline above the harbor surface, creating a pumpable volume. If a ship cannot rise to the surface, the engineers must artificially lower the surface to the ship. This is the mechanical logic of the cofferdam. The Salvage of the USS California required the construction of a massive wooden fence, built directly onto the submerged quarterdeck and forecastle. The objective was to extend the vertical sides of the hull until they broke the surface of the Pacific. Once this wooden extension was watertight, the pumps could lower the water level inside the fence, creating a dry volume where buoyancy could be restored. The construction of this barrier was a feat of underwater carpentry performed under zero visibility conditions. Divers had to bolt heavy timber sections to the steel gunnels of the battleship. The connection point between the wood and the steel had to be tight enough to hold back the pressure of the ocean. This was not a standard construction site. The hull was listed, curved, and coated in slick fuel oil. The divers worked by touch, drilling bolt holes and setting seals in a blind environment where a single gap would render the entire pumping operation useless. While the carpentry teams built the walls above, the patch teams addressed the torpedo damage below. Standard salvage procedure uses a flat timber patch, a rigid box made of wood and canvas that is bolted over a clean hole. But the damage on the California was not clean. The torpedo impacts had torn the steel plating into jagged, irregular shapes that defied standard measurement. A flat patch would not seal a three-dimensional wound. Salvage crews used a combination of cofferdams, internal closures, and localized sealing methods for leaks and irregular openings. The goal was to get pumping capacity ahead of the remaining inrush. This technique converted a jagged structural failure into a rigid, watertight plug. This was the difference between a soft collision mat, which might fail under pressure, and a hard engineering solution. With the cofferdam completed and the hull patches set, the dewatering phase began. The team deployed massive 10-inch centrifugal pumps. These machines were capable of moving thousands of gallons of water per minute. As the engines roared to life, the water level inside the wooden fence began to drop. The pressure differential grew. The ocean pressed in against the timber walls with thousands of tons of force. The divers monitored the structure for leaks, listening for the hiss of incoming water and plugging gaps with oakum and wedges. The system worked. The interior water level dropped, exposing the main deck for the first time since December. But as the water receded, a new problem emerged. The ship was no longer flooded, but she was not floating. The pumps were removing the water weight, but the California remained firmly stuck in the mud. The engineering calculation revealed the next constraint. The ship was simply too heavy. The displacement generated by the pumped hull was not enough to overcome the dead weight of the armor, the machinery, and the suction of the harbor bottom. The cofferdam had created a dry hole in the ocean, but it had not created a floating ship. The salvage of a battleship is ultimately a balancing act performed on a massive scale. On one side of the equation is the downward force of gravity, pulling the steel structure into the seabed. On the other side is the upward force of buoyancy. For the USS California to rise, the engineers had to manipulate these variables until the upward force exceeded the downward weight. By late March 1942, the pumps inside the cofferdam were removing water, but the math remained stubborn. The ship was still too heavy to break the grip of the mud. To alter the equation, the Salvage Command ordered a radical reduction in the ship's basic mass. This was not a preservation effort, it was a demolition operation. The massive 14-inch guns of the main battery were extracted from their turrets. Ammunition, anchors, and chains were hauled away on barges. Every ton of steel removed from the topside was a ton of buoyancy gained for the hull. The most visible casualties of this weight reduction program were the ship's distinctive cage masts. These intricate lattice structures were designed to hold fire control directors high above the smoke of battle. Now they were simply dead weight. The engineers did not have the time or the crane stability to carefully unbolt the complex lattice work. Instead, they treated the masts as structural scrap. Burning teams cut through the heavy steel legs with torches, slicing the structures free so they could be lifted off in single massive pieces. This was a decision driven by the load limit, not sentiment. The masts had to go so the hull could rise. As the weight came off and the water level dropped, the salvage team faced a new instability known as the free surface effect. This phenomenon occurs when a compartment is partially filled with liquid. When a tank is full, the water acts as a solid weight that moves with the ship. But when a tank is half full, the water is free to slosh from side to side as the ship rolls. This movement shifts the center of gravity dynamically, creating a momentum that can capsize a vessel in seconds. The California was full of these free surfaces. As the pumps lowered the water in the engineering spaces, the remaining fluid was free to rush across the wide operational decks. The engineers had to manage the pumping sequence precisely to prevent the water from accumulating on the port side, which would have exacerbated the existing 5.5-degree list. They used the residual water itself as a counterweight, trapping specific volumes in starboard voids to force the ship toward an even keel. It was a fluid balancing act, fighting the list while simultaneously trying to lighten the load. By the final week of March, the calculations suggested the ship was ready. The main battery was gone, the masts were cut, the internal water volume was reduced to a managed level. The cofferdam was holding back the sea. However, the ship remained stationary. The static friction of the harbor bottom was the final variable. The hull was not just resting on the floor, it was embedded in it. The engineers had solved the weight problem and the water problem, but now they had to break the suction of the mud itself. On the morning of March the 25th, 1942, the salvage operation entered its critical operational window. The mathematical model indicated that the USS California had achieved positive buoyancy. The weight of the steel removed from the superstructure, combined with the thousands of tons of water pumped out of the hull, meant the ship was now lighter than the water she displaced. By the laws of displacement, she should have been floating. She was not. The vessel remained pinned to the harbor floor by a phenomenon known in salvage engineering as mud suction. When a flat-bottomed ship settles into soft sediment, the mud creates a perfect seal around the perimeter of the hull. This seal prevents water from flowing underneath the keel. Without water underneath the ship, there is no hydrostatic pressure pushing up against the bottom plates to counter the gravity pushing down. The ship effectively becomes a suction cup adhered to the earth. To break this bond, the engineers must apply a force significantly greater than the weight of the ship alone. They must generate enough upward lift to rip the hull free from the sediment gasket. The team continued to run the 10-inch pumps at full capacity, lowering the internal water level further to maximize the pressure differential. This phase carried a specific risk regarding the hull patches. While the concrete patches were rigid, the divers had also employed thrummed collision mats to seal smaller, irregular shrapnel holes. A thrummed mat is a heavy canvas sheet tufted with rope fibers, designed to be sucked against a hole by outside water pressure. However, in this transitional phase, the pressure dynamics were volatile. If the pumps lowered the internal pressure too aggressively, or if the external seal against the mud shifted, the flow dynamics could invert. A soft mat intended to sit on the outside of the hull could be sucked violently through the jagged aperture and into the ship. If a mat failed or inverted, the resulting inrush of water would destroy the buoyancy calculation instantly, potentially dropping the ship back into the mud with enough force to shatter the timber cofferdam. The engineers maintained the pumping rhythm, monitoring the mats and the water levels. At midday, the physics finally aligned. The buoyancy force overcame the adhesive friction of the seabed. The mud seal broke. Water rushed into the vacuum beneath the keel, restoring the upward hydrostatic pressure. Slowly, without fanfare, the bow of the California lifted from the bottom. The rise was not immediate or even. The ship hesitated, then lurched upward as the suction released its grip section by section. The salvage master ordered the pumps to balance the flow, correcting the list as the hull sought its natural equilibrium. For the first time in 3 months, the USS California was no longer a wreck connected to the Earth. She was a floating vessel again. The cofferdam had held. The patches had held. The ship was afloat, riding on her own bottom, ready to be moved. But while the external battle against gravity was won, the internal atmosphere remained a dormant threat. The ship was up, but the chemistry inside her compartments had not yet finished its reaction. On April 5, 1942, the USS California offered a final demonstration of the volatility inherent in marine salvage. The battleship was afloat. The cofferdam had done its job, and the pumps were maintaining equilibrium. The difficult engineering work of the lift was theoretically complete, but the internal chemistry of the vessel remained active. At 13:15 hours, a violent explosion shook the forward section of the ship. The blast was not caused by enemy action or ordnance, it was caused by the very atmosphere of the ship itself. The mixture of fuel vapor and hydrogen sulfide gas, trapped in a fuel tank, had found an ignition source. The overpressure from the blast blew out the temporary patch sealing the original bomb damage on the starboard side. The ocean immediately rushed back in. For a few critical minutes, the California threatened to undo 3 months of labor and settle back into the mud. The salvage crews, wearing their protective masks, had to scramble to reseal the breach and restart the pumps. This incident, occurring after the ship was technically saved, served as a validation of the risk assessment made weeks earlier. The gas hazard was not a theoretical constraint. It was a physical force capable of sinking the ship from the inside out. The crews contained the flood. 4 days later, on April 9th, the California was moved into dry dock number 2. This was the definitive end of the salvage phase and the beginning of the industrial phase. As the caisson gate closed and the dry dock pumps drained the basin, the true extent of the damage became visible in the open air. The hull was scarred by torpedoes, the steel plates warped and torn. But the most significant damage was invisible from the outside. Inspection and overhaul revealed severe machinery and electrical damage requiring extensive repair and modernization before the ship could return to service. The saltwater intrusion had corroded the massive electric motors and generators that drove the 4 screws. This technical reality dictated the ship's future. The California could not simply be patched and returned to the line. She required a complete reconstruction. The Navy did not just repair the ship, they evolved her. Because the entire machinery spaces had to be gutted to replace the electric drive, the shipyard took the opportunity to strip the vessel down to the deck. The heavy tripod masts, the old casemate guns, and the outdated superstructure were removed. In their place, the engineers built a modern, streamlined battleship centered on anti-aircraft defense and fire control radar. The hull that was dragged out of the Pearl Harbor mud became the foundation for a virtually new warship. The salvage operation did not restore the California of 1941. It provided the raw material for the California of 1944. The success of the operation was not measured by the restoration of the past, but by the preservation of the asset. The constraints of mud, weight, and poison gas were overcome by a disciplined adherence to physics and procedure. The ship that was once a toxic, sunken obstacle was returned to the fleet, proving that with enough engineering leverage, even a 32,000-ton loss can be reversed.